Yeah, so last time we've considered the Hermite polynomials, and we found that their moments are basically the number of Hermite histories which are in bijection with complete matchings. We will do similar things with Charlier polynomials. So let me begin with the definition. The normalized, from now on, we will be considering just the normalized versions. And like I said last time, if you look at Charlier polynomials in some other literatures, they may not be written exactly in this form, but you can rescale them so that we get our version. So the normalized Charlier polynomials, which we will write as cis n, x, and a, are defined by this recursion. With the usual initial conditions that the zeroth polynomial is 1 and negative 1 index polynomial is 0. Okay. So in other words, here bn equals n plus a, lambda n equals an. So here a is a parameter. It can be anything. So unlike the Hermite polynomials, bn and lambda n are not integers, but we have some parameter like this. This can be anything. So we will consider these as polynomials in A. But just imagine that a is 1, then this is an integer, this is an integer, right? So in that case, we can define something similar to Hermite history. So here is the definition of a Charlier history. So again, this is a Matchkin path, labeled Matchkin path. Matchkin path where we have a label. Let me just explain them using just a diagram of step. Each horizontal step, height k, has label here, let's say I, label I in one of these integers. So we have k plus 1 choices for the label. And when we have a down step with starting height k, we have a label 1 up to k. Okay. So that's exactly the number of possible choices is k plus 1 choices. So here we have k plus 1 choices, and here we have k choices. Okay. And C Charlier history sub n is the set of all Charlier histories from the origin to n comma 0. So length n Charlier histories. If just a equals 1, then the moment of the Charlier polynomials will be, this is our combinatorial model for the moment says that sum over all Matchkin path of length n, we add the weight of pi, where weight is, here this weight is that if you have a horizontal step at height k, we multiply bk, and when we have horizontal down step starting height k, we multiply lambda k, right? But bk, what is bk? Bk is k plus a, but a equals 1 in this example. So this is a times k, but if a equals 1, that means you multiply k for this, multiply k plus 1 for this. That means you have exactly this many choices for each horizontal step and this many choices for each down step. So that will give you exactly this. Okay? But the problem is a is not 1 in general. So how can we do this in the general case? This is easier. You see, you can just multiply a for every down step, right? But for horizontal step, we have k plus 1. That means if you just assign, say it is 0 looks a little different from the other. So if you have a horizontal step of label 0, then we just say that we multiply a there. Then that will be exact, give us a combinatorial model for this. So we, in general, mu n is sum over pi. I'm just writing this. So this is sum over all. Let me write rho for Charlier history. A multi to the let me just write t of rho, where t of rho is the number of horizontal steps with label 0 plus number of down steps. Because for every down step we multiply a, and among k plus 1 choices we multiply a if the label is 0. That will give us only one possible choice for a. So this is the first observation that we have. Okay. But let me give you an example. Just so example. Up, 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 down, down. Oh, not this one. It's a Hermit history. Up, horizontal, up, horizontal, down, down, up, down, horizontal. So up steps, they all have a weight. They don't have a weight, so you can forget about them. So this is height 1. So we have two possibilities, 0 or 1. But let's say we have a weight 0. And here we have, for this we have 3 choices, but let's say we have label 2. And here 2 choices, but we chose 2 and 1. Only one choice here, and only 0, 1 choice for that. So in this case, what is t of a? So let's say rho is this. What is t of rho? You basically you count all zeros and all down steps. So we have 1, 2, 3, 4, 5 horizontal steps of weight label 0 or down step. So this is going to be 2 plus 3, 5. Okay. So in this sum, this will contribute a to the 5th. Okay. So if you add all of these weights for each Hermit history, you will get the moment the moment of the Hermit polynomials. Okay, that's the setting. All right, and now I think I will use this later. So let me copy. And before, if you remember, we constructed a map between Hermit history and some diagram which represent complete matching. And similar to this, we will have a bijection, similar bijection like this. Recall that this is the set of all set partitions. So set of all set partitions of n. Okay. And for set partition sigma, say, define block of sigma to be the number of blocks in sigma. Okay, so the quite natural definition. And we have this theorem. The moment of the Charlier polynomial is the generating function for all set partitions with this block. This is a theorem that we will prove. So how can you prove this? So we already know here. We already know this. So we need to find the bijection between sufficient to find a bijection, say phi from Charlier histories to set partitions, such that if you have a rho mapped to sigma, then we want the t number equals the number of blocks, because then mu n is rho in Charlier histories a to the t. But if we have such a bijection, this will be equal to sum of all sigma a to the block, because this bijection guarantees that there is a one-to-one correspondence between the expansions term by term, so the sum must be the same. So this is our goal. So we will find a weight preserving bijection like this. But the map is quite similar to the one that we saw before, so it shouldn't be that difficult. But let me just give you an example. So suppose that we have a row here, and it'll be as before. For each step, we will create a dot. For each step, create a dot. And of course, each dot will be assigned a number like this. Okay. And for an up step, put an opener. Up step. So up step corresponds to an opener. So opener, let's say. And down step will correspond to a closer like this. And what about the horizontal step? If the horizontal step has label 0, then it will be just a singleton. And if it has weight something different from 0, then we will have a local configuration that looks like this, which we will call just transient. Okay, so we make a local configuration like this. So this is 0, so we don't put any half edges here. But this is an up step, so it's an up opener, and this is going to be transient like this, and closer, up, opener, closer, and nothing there. So we have this local configuration like this. All we need to do now is to connect the openers and closers along with the transients. The idea is really simple. So we go from the beginning, and then we look at the first closer. Then we're gonna connect this with one of these available edges according to the label in the corresponding step. So this is 2, then we will just simply connect the, if this is k, we will connect this with a kth closest available arc. So first we have 2 possibilities. This is 2. So second closest. So we're gonna connect this with this like this. Okay. Is it okay? And then this is done. Now we just proceed to the next closure here. Closure or transient. This is, now the label is 2, so we connect the second closest available arc, open arc. So we have 2, so we this is the second closest, so we connect this with the second one like this, and so on. And this is label 1, so we connect this with the first closest available arc, open arc, so it's like this. And so on. And you see we have to connect this, and then that's it. So we get a diagram like this, but this represents a set partition, right? Because each block is just a connected component like this. So this is really a set partition 1, 4, 6, and 2 singleton, 3, 5, 7, 8, and 9 is a set partition. Of course, we have to collect them all. This is a set partition in pi 9. This is a bijection. Yeah, if you think about it, yeah, you're convinced that this has to be a bijection. But what about the property that we need? Why is this true? If you think about the structure of this bijection, the construction of the bijection, this map, then this should also be quite clear. When do we get a block? When do we create a new block? Or maybe when do we complete a block? When do we complete a block? If we have a singleton, it itself forms a block, so that means this will create a block. And opener, we will focus on the time that a block is completed. So this does not complete any block. This will complete a block. So this we get one block for each closure. So each, or in other words, each down step. This is transient, is not completed yet. So we get a block whenever we see a down step or horizontal of label 0. So that's exactly this. So that's why this is the truth. And that's basically the proof. That's the proof. If you understand the structure of the map, then it should be clear that it's a bijection, and also the property. One thing that you may want to notice is that the label, the height is always the number of available arcs. So the one thing that one observation that important observation is that height of each step is the number of available open arcs. So if you have an opener like this, then height is increased by 1. You have one more available opener, and this will close one opener, so it will decrease the number of available openers, and this does not change any available openers, and this does not change any, it keeps the same number of available openers, so that's why we have things like this. That means the labels, the label is always less than or equal to the starting point, the height of the starting point, so we can always connect the dots in this way. So the web map is well defined, and this can be also, the inverse map can be constructed similarly. Okay. Yeah, so that's the combinatorial model for the moment of Charlier polynomials. So Charlier polynomials, their moments correspond to set partitions. Okay, now let's move on to the next section. So Laguerre polynomial. As you can notice, as we go further and further, we have objects just more complicated. So we have more structures there. So Laguerre polynomials, they will be more complicated. But the basic idea is similar. So normalized Laguerre polynomials. Laguerre polynomials, which we will denote by n L of n superscript alpha x are defined by the following recurrence. So it should be just a regular n, regular L, and L minus n minus 1 plus alpha, like this. So in other words, what is Bn? 2n plus alpha, lambda n minus 1 plus alpha. Again, alpha is a parameter, so it can be anything. So we can start with the original combinatorial model for the moment using the Matchkin path, weighted Matchkin path with b's and lambdas. But we will modify that combinatorial description a little bit using this lemma. Suppose that we have an OPS. So OPS, monic OPS, is a monic OPS such that three-term recurrence looks like this. Pnx minus a minus 1 cn p minus 1x. So in other words, our lambda n will be a product of two numbers like this. The index looks a little weird, but the reason will be clear later. Then we have this combinatorial model, slightly different combinatorial model. So Matchkin path is still the same, but we have a different weight. What is this? So here, weight prime is the product of weight of steps in pi. We'll have to define the step, the weight of each step in this way. So let's say we have this height k. So we have an up step, starting height k, and also we have horizontal step with starting height k and down step with starting height k. We always look at the starting height, okay? And this has weight ak, this has weight bk, and this has weight ck. That's the definition of the weight of each step, okay? Now that's the statement, and let's prove this. Proof. We know that this is our usual weight. We know that it should be this, where up step has always weight 1. Maybe I can just use the same height. This has weight bk, and this has weight lambda k, which is ak minus 1 ck. Okay? This is original combinatorial model. But maybe I can just give you an example. But whenever we have a Matchkin path, every down step is corresponds to a unique up step. Like we draw a tunnel like this. For each up step and down step, they are matched together like this. Every up step corresponds to a down step, and they're at the same level. So initially we have, maybe I can just copy this. So initially, our weight here is our weight here, weight prime, is like, this is lambda 1, which is A0, C1. This is lambda 2, so A1, C2, right? And here is A0, C1. I'm putting a weight only for the down steps and horizontal steps, A1, C2, A2, A2C3, and here is B1, right? This is our original weight. But now it should be clear to you what we are going to do. We just move this weight for A to the corresponding up steps. Just separate this like that. So this will get A0 there. So C2, C3, A1, A2, and this A0, A1, C2, C1 like that. Obviously, their weights are the same because weight is the product of the steps. And the weights are exactly like this. Initially, our weight looks like this, but if you move this over here, then it's going to be k minus 1 because the starting point, the ending point is k, height k. So the starting point has height k minus 1. So in other words, weights are given like this. So they are really the same. That's the proof. Yeah, it's quite simple, right? So in this way, we can distribute the weights to both up steps and down steps. Sometimes it's useful. So we will use this new combinatorial model. All right. So because of this lemma, maybe I can just. So in a Laguerre case, we have this, or so we're gonna say that this is Cn, this is Am minus 1, so that in other words, mu n is going to be sum over all Motzkin path, weight prime, where what is ak? This with actually this should be k plus alpha, bk equals 2k plus alpha, ck equals just k. So this is our model now. Again, we're gonna create labeled Motzkin path, similar to Hermite histories or Charlier histories. But of course, the name should be Laguerre history. What is a Laguerre history? Is again a Motzkin path where before we labeled only horizontal and down steps because they have weight and up steps always have weight 1, so we didn't label the weight up steps. But we're gonna label the up steps together, where first up step, so here is height k. Yeah, let me draw a little like this. This has label I from 0, 1, 2, dot, 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 k. We want the number of choices to be this, where alpha equals 1. So we want the number of choices to be k plus 1. So we label like this. Possible weight, the possible weight, the number of possible weights is k plus 1. And what about down step, horizontal step of height k? Here the label, say I, the label, the number of choices should be 2k plus 1. But for some reason, we will write minus k, dot, 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 minus 1, 0, 1, because this is nice 2k plus 1 numbers. Okay? But the choices can be anything. But this will be this will be easiest for us in our description. So that's why we use that. So here, this label, there are k choices, so the natural choice would be this. Okay. So again, if alpha is just 1, then this will be just the number of Laguerre histories. But alpha, we want to keep alpha together, then how can we keep track of alpha? So for every up step, only one choice will give us alpha, right? And for every horizontal step, only one choice will contribute alpha. So yeah, this 0 looks interesting, so we can just keep track of zeros, right? So let's, LHN is a set of Laguerre histories. From 0 to n. And for Laguerre history row, we define 0 of row to be the number of steps with label 0. Up, it could be horizontal or up steps, right? You just look at just the number of zeros there among the labels. The down step can never have label 0. So then the moment of the Laguerre history must be sum over all Laguerre histories alpha the 0 of row. This is what we can get. This just follows from our construction. Okay? If alpha equals 1, this is number of Laguerre history as we observed, but for general alpha, we can still keep track of the alpha. Okay, so now what should we do? These Laguerre histories are in bijection with permutations. So we will construct permutation, bijection. So our goal, find the bijection. Phi from Laguerre histories to the set of all permutations with a nice property such that if a row is mapped to, say, sigma, then 0 is equal to the number of cycles, cycle of pi. This is the number of cycles in pi, in sigma. Okay, this is our goal. But just imagine that we have such a bijection. Then if this will imply what? Mu n equals sum over all sigma alpha to the cycle of sigma. But do you remember what this is? So it has a nice formula, right? It is alpha plus 1, dot, 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 alpha plus n minus 1. So we already proved this. This was, we did this before. So we have a very nice product formula for the moment of Laguerre histories. Sorry, Laguerre polynomials. So now we need to find a bijection like this. That's what we're gonna do now. There are actually two bijections, but I'm gonna explain. If we have enough time, I can explain the two bijections. But let me first explain the first bijection. Okay. So bijection 1. It's called, this is due to Franson-Vienno. So Franson, this is a French character. Franson-Vienno. This is original equivalent to Franson-Vienno bijection. Okay, so to do this, so we want to find a bijection like this. Sn. So first, okay, let's say rho is in LHN. So we have a Laguerre history, so we want to make a permutation out of this. And okay, how shall we do this? So we will look at okay, maybe I think it's easy. It can be explained the best using an example. So I'm gonna explain this map using an example. So our running example will be something like this. So it's the Laguerre history, so we have to put some weight. And so up step may have weight here. We have actually only one choice. Here we have two choices, 0 or 1, but say we put 1, and here is this is the one choice that we will consider. It's -2, 3, 2, 2, 1. So this is our Laguerre history. Okay. So the idea is we consider k from say 0, 1, 2, ... and we will for k we will construct a0, a1, ... an, which are list of cycles. So we at the end we want a permutation. So permutation can be written as a product of cycles. So we will build a list of cycles. So at the end we will get a permutation. That's the idea. So the first, this is empty. There's nothing. So we start from nothing and then we build. We insert one object at a time, one number one at a time. So case 1. So we have k like this. So k equals 0, then we have this. And now we suppose ak minus 1 is constructed. And we will build ak recursively in this way. So first, let's say kth step is an up step. Let me just write u. Of course, the case step means a step in our Laguerre history. Okay. Then so like this, just like this. Then we have to consider two cases. If with the label, say L sub k. Okay, the k label of the kth step. If L sub k equals 0, and if L sub k is different from 0, so greater than 0, we will consider two cases. then in this case, AK will be AK minus 1. We insert something that looks like this, K and some dot. So we have some dots. So that will be there in the process, but at the end there will be no dots, so we will get a complete cycle. Okay. So think of this as a cycle that needs to be completed. It's a cycle, open cycle, something like that. So we have to complete this cycle in the process. And if the label is greater than 0, so say I, then AK minus 1 is a list of cycles, so, and there could be several dots. So we have several dots. I don't know exactly, but we have dots, something like that. And let's say this is the ith dot. Okay, so suppose that this is the ith dot. We're gonna replace this by K with dots like this. Does it make sense? I guess not. So I'm going to explain with an example. So here, what is A0? A0 equals empty. What is A1? The first step, I think it's nice if I can just put 1, 2. I'm going to label the step like this. There are 11 steps. So the first step is an up step, and what is this label? It's a 0. So that means we insert a cycle, incomplete cycle like this. So it will be 1, nothing, or some dot. That's it. That's A1. Okay. And what about A2? Again, it's an up step. So, but the label is not 0. So we have this situation. So it's 1. So there are a bunch of dots, actually only one dot. So we replace the first dot here with something like this. So this will be replaced by 2 and dots like this. Okay? So we do things like that. And actually, it might be helpful. Number of dots will be starting height, so that we can do this. This will be clear the process. So this is case 1. What about case 2? The kth step is horizontal with label LK. Then what are the possibilities? We can have either negative numbers, 0, or positive numbers. So we will consider 3 cases. So case 1, if LK equals 0, if the label is 0, then AK will be AK minus 1. We insert a cycle, but there's a complete cycle of length 1, like this. So, and if if label is positive, then ith dot, just like this, is replaced by K dot. And if the other way around, it's minus I less than 0, then ith dot will be replaced by dot K, like this. So we keep the number of dots, so one dot must still be a 1 dot, but there are 2 possibilities with a dot locate is to the left of K or right of K. So let's look at the example here. So what is A3? So the third step is a horizontal step, so it's one of this, but the label is 0. So then we create a cycle like this. And this is still the same. Okay. And what about A4? We do not know that yet because we have to define. But let me. Okay, I think I'll. Yeah, maybe it's too. Maybe we can keep the space in this way. Maybe I should write things a little small, like this. Okay, so case 3, kth step is down with label LK. But LK is always positive. Down step has always positive weight. Okay. Then actually it's quite simple. I think this is replace ith dot by just k, no dot. So we lose one dot, and then you see if you have a down step, the height is decreased by 1. So we decrease the number of dots by 1. So it's always, if you look at the step, we always have this situation. So whenever you see an up step, the number of dots is increased. It's increased. Oh, sorry. Up step, number of dots. Oh yeah, right. Here we have 1 dot but 2 dots. So number of dots is always increased by 1. But here the number of dots is still the same. The plus 1, but it's not. But there is a minus 1. So this is always true. So now we can complete the picture. Maybe it's, we have enough space there. So A4. Oh, I think we have enough space. So let me just move this back here. That'll be easier to follow. So A4 is a down step. So it's a label 1. So we have first and second dot. So we replace the first dot with the number 4. 1, 4, 2 dot. Okay. And then what about A5? A5 is up step. So it's like this, but the label is 0. So we create a new cycle with 5 dot. Now you see you can proceed. 6 up step, but is greater than 0. Label is greater than 0. So we replace 1, 2, the second dot with things like this. 1, 4, 2, and 6 are dot dot. And then A7 horizontal, but the label is minus. So it's a minus 2. So we look at the second dot, the first second, and replace this by this. Second dot will be replaced by dot 7, 6 dot, and then so on. A8. 3, third dot, so 1, 2, 3, so it will be 1, 4, 2 dot 7, 6, 8, and 9. So horizontal, so positive weight. So it's this. This. I think the first time it appears. So 1, 2, we replace that by 1, 2, 1, 4, 2. So 7, 6, 8. We replace this dot by positive weight. So this 9 dot. Okay, and so on. So now it's we need to complete the picture. So this second. So first, second. 10 10, 7, 6, 8, and finally 5, 11, 3, 1, 4, 2, 9, 10, 7, 6, 8. So this is a cycle decomposition of a permutation. So this is really a permutation. So this is our map. Yeah, this is, I think, less clear why it's a bijection than the previous two maps, but if you think about it, it should be straightforward to check there's a bijection. But let's check whether we have this property that we want. Why the number of zeros equals the number of cycles? Just look at the situation where we create a new cycle. When do we create a new cycle? We create a new cycle in this way. So this is when we get a new cycle. So you see this is 0, so new cycle. And also here, this is 0, we get a new cycle. And other cases, we don't change the number of cycles, it's still there. So this, at least this is clear. The number of zeros is clearly the number of cycles of the permutation. And because of this is well defined. We can always find the ith dot, and then we can replace that as described here. So the problem is, how can we go the reverse process? But to do the reverse process, but actually, if you know how to write permutation in this way, then actually going back is not that hard, because suppose that you have the diagram like this. Then each time you go back, you just replace the, the largest number by a dot. So here this just became a dot. So 10 became a dot, 9 became a dot. But once you have a dot together, that's a single dot, like that. So see here, dot, 7 became a dot. So say this become this, and etc. So once you have this, you can go backward. That's not that's easy. But if you know all the sequence like this, then the mapping between these is not that hard. Okay? So the problem is, how can you write a permutation in this way? Because a permutation, there are many ways to express permutation as a cycle decomposition. Because first of all, a cycle, even for one cycle, there are many ways to express the cycle. Because cyclically shifting a cycle is still the same cycle. But you see, the construction here, every cycle, the smallest number must appear at the beginning because of the construction. Whenever we create a new cycle, the starting element is k, but the other element will always be greater than k because we insert integers k at stage k, again over here. So the first element is always the smallest element in a cycle. So in our, what I'm saying is, if we have a permutation, we express pi as a product inside, let's say in cycle notation. Such that every cycle first starts with the minimum element, mean element in that cycle. Okay, we can always do that because cyclically shifting a cycle is the same thing. And so the mean elements are okay, but what about how can we order the cycles then? Again, by the construction here, whenever we create a new cycle that is placed at the beginning, that means these must be increasing, in this way, or decreasing in this way. So in other words, cycles are ordered so that the mean element are decreasing, right? Just like this, decreasing. But if you impose these two conditions, then there's a unique way to express this. And we can express uniquely with this condition. That means if you have a permutation, you can write the permutation cycle in the cycle notation uniquely in this way, and then you can go back, and this will be a bijection. You can, if you think about this long enough, then you'll be convinced that it will be a bijection. Okay. Okay. Yeah, and one nice thing about this bijection is that this, in fact, contains the two bijections that we saw before for Hermite histories and Charlier histories. So let's see why that's the case. Note the bijection phi from Laguerre history to permutation actually contains bijection, let's say phi1 from Charlier history to set partitions, and also bijection from Hermite history to complete matchings. Why is that? First of all, let's compare Laguerre histories and Laguerre histories and Charlier histories. So the up steps have no weight. So that means we can just say that every up step has weight 0. Okay, so we can forget about the weight of an label of an up step. And horizontal step, we have actually minus weights here. But if you forget about the minus weights, then we always have positive weight. Okay, so if every let me put this in. In fact, see, this is actually contained in Laguerre histories, where such that row has in row, okay, such that in this way, in this sense, let's say row in row, every up step has weight, fixed weight 0, and every horizontal has weight greater than or equal to 0, and this is the same. Then this is exactly Charlier history. Then what are the corresponding cycle, cycle list? So see, we don't have this. So we always have this. So this is like creating a new block. And what about this? This is okay, but this is not allowed. That means every cycle, it always looks like something and dot at the end, always at the end. Because we don't have this situation, we don't have a situation like this. That means we have a cycle, always we add a number at the end. That means a cycle, the integers are in increasing order. So in this case, every cycle is in increasing order. That means we can forget about the order, and then we can just make it just a block. So by making blocks, by making cycles to block, we get element in Z partition. Or maybe I think I denote this by sigma, right? So we can just treat a list of cycles as a Z partition. Okay, so that's exactly bijection between Charlier histories and Z partition. Okay, then what about this? Hermite history can also be considered as a Laguerre history, where every up step has, again, weight 0, and this there is no horizontal step, and down step weight the same weight, yeah. Same. But in fact, this is also a subset, or maybe I can even write as a chain of something like that, right? Then what happens? We don't have this, but horizontal step, this will make our cycle longer and longer, but that's not allowed. So once you started a cycle like this, you have to immediately finish it once you fill this stuff. That means every block is of size 2. So in this case, every cycle has length 2. That means you just basically connect, you just find the matching, complete matching on complete matching. So this bijection contains everything that we saw before. Okay. So that is one bijection that I explained, but we have a little bit of time, so let me give you another bijection. But you may prefer this bijection because this really uses the arc diagrams that we saw. So it should be easier to understand. But keeping track of the correct weight, we have to do extra work. But I'm going to explain only the bijection without worrying about the alpha weight. So this bijection is due to Forata-Zeilberger. But we're gonna use the original Marchkin path weight. We use the original weight for Marchkin. Okay. That means, and we will only, for simplicity, we'll assume that alpha equals 1, just for simplicity. Okay. I'm going to just give you a bijection. And what is Bn? Bn is, maybe Bk, is the weight 2k plus 1. And lambda k equals k squared. Alpha equals 1. That means for every horizontal step, we have a choice minus k minus 1. This is the same. 1k. And for down step, instead of just giving k squared, I'm gonna think of this as a pair of integers, ij both. So it's a pair like this, ij both 1 up to k. Then the moment will be just a number of, let's say modified Laguerre history. Okay, then mu n is going to be a number of modified Laguerre history. Okay, so we will find. I'm gonna just show you example, and I'm gonna skip the details, but you can fill in the details. It's okay. Let's see. We have an example like this. Say 0, 2, 1, minus 2, 3, 1, 2, 1, 2, 1, 1. Okay, so the idea is, the question actually is, how can we represent a permutation like an arc diagram? But before that, let me just draw this as usual. So it's going to be, we have one dot for each horizontal step, each step. And we're gonna put a local configuration as before, but the local configuration will look something like this. Before, we had something like this for an opener and closer, but we have something like that in two directions, up or down. And we may have a singleton, or we have a local configuration like this, like a transient, and this negative version like this. We will have this. And up step, we will have opener. Up step, opener. 0, nothing. So this will be 0. And down step is always closer. Up step, always up. And if we have a negative weight for a horizontal step, I'm going to put transient, but below the line. And here's up step, closer. And this, for positive label, horizontal step like this. And finally, down, down. And then the idea is similar. We connect this with this for the upper arcs, this for the lower arc. So we have two. We connect this with the second closest opener above, and the first closed opener and below, like this. And here, if this is minus, then you use the thing below, and the first and second. So connect first and second like this, and so on. And 3, this first coordinate will be for upper arc. So 1, 2, 3. So this connected to this, and first like this, and then 2 connect first and second. So like this, and 1. So this 2. So with 1, 2. So this. Finally, this and this. So we have a diagram like this, but this represents a permutation. So let me put the label. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The idea is, so if you have a permutation in a two-line notation, you have something like this, right? Then if I is smaller, then we put arrow like this above. But if I is less than, if I is here, if I is bigger, then we put arrow like this. But actually, we don't have to put the arrow. This is always arrow. This is always arrow like that. This is always arrow like that. And this is a bijection between 1 up to n to itself. So it's a permutation. Every permutation can be written in this way. Of course, this is a singleton, so it's a fixed point. And if you think about this, this is really is similar to the bijection that we saw for Hermite histories and also for Charlier history. So it should be clear to you that it's a bijection. But this does not have the property that cycle structure. So but instead of cycle structure, we can consider something different called like a left to right maxima. But yeah, I'm not gonna tell you the details here. But there will be some homework problem related to left to right minima, so you can think about them later. Yeah, so we have these two bijections for Laguerre history. So yeah. So we have seen so far three special orthogonal polynomials: Hermite polynomials, Charlier, Laguerre, and there are more polynomials out there, but there are also studied regarding those polynomials. But even though they have similar structures, there are more complicated weights, but the way the philosophy is similar. Okay, so I think I can stop here. Thank you for your attention.